today's the last section, but we are going to spend at least 2 hours, 3 hours on this section. Okay, we're trying to solve an inverse problem. Remember, if the power series is convergent, you get a function defined on that called interval convergence. Okay, so and you get a nice function, and sometimes the function you already know that it's just like a you know, it's going to be 1 over minus 1 over 1 minus x. So that's the one direction, right? So if yeah, if you consider, let's see, that's what we learned. Okay, we suppose, yeah, suppose there's this power series is convergent, okay, on the interval a minus capital a plus capital. Okay, so here we, you know, a is I is radius convergence. Okay, then we get a function. Okay, so this is a nice function defined on this interval. But it's possible this function can be extended. But it's possible the function f of x can be extended to a larger interval. Okay, that's possible. Okay, but it's not going to be equal to this power series on a larger interval. The reason is the interval the series is not convergent. Okay, so let's look at example, the following example. Okay, we consider this series. So this is our example already discussed many times. Okay, so consider this power series. We don't know what is that, right? It is convergent on the interval from negative to positive. So it defines a function. So I let fx to be, okay, I know it's convergent. Okay, so I get a function on the interval. Then later on I find that, oh, that function is not a brand new function. It is actually is nothing but just 1 of x, right? Then later we find out, and in fact, f of x is just 1 over x. Okay. If you express fx in this form, then clearly this f of x can be extended to a larger interval, at least from negative infinity to 0. Okay, but away from negative 1 on the left hand side, the function cannot be expressed as the above power series. So fx can be extended to, right, from negative infinity to positive 1, right? But 1 minus x is not going to be this power series on this interval. Okay. Right, because the one on the right hand side is not going to be convergent. Okay, so be careful. This is a yeah. Yeah. So we are given power series, and the power series define function fx, and blah blah blah. After compute, because this is special power series, after do the computation, we find out this power series is convergent to, okay, a very nice function, which is 1/1 minus x over the interval from negative to positive. Then you say, okay, this is a 1/1 minus x. This function itself is defined from negative infinity to positive 1. But away from negative, on the left-hand side, the function is defined. Yeah, it's 1/1 minus x, no problem, same formula. But that's not going to be given by this power series, okay? All right, it's not going to be equal to the power, because the power series is divergent. This time, here it is divergent. Cannot say they're equal, okay? It is divergent on that interval. All right. So what kind of function can be expressed? The next question, given a function, right? We want to find its power series representation, okay? We want to, I want to talk about directly. I don't want to separate, Taylor series and Maclaurin series. And Maclaurin series is just a special Taylor series, right? So, so given a function f of x on some interval, okay, on some interval I, okay, and a number in the interval I, okay, so such as some interval here and here's a, okay, and how do we know? Can we express it as a power series? Okay, and then so that they're equal in a small neighborhood. Okay, can we, yeah, how to determine, okay, how to determine whether or not this function is expressed as power series, okay, how to determine, yeah. Yeah, so the question is, can fx be expressed as a power series, okay, over some interval a minus capital, a plus capital, okay, and how to find it? How to find the power series representation, okay. Okay, so we want to study this problem. So the question is how to determine this constant Cn, right? And whether they're equal in some interval. That's two problems. But for function 1/1 minus x, we already get a nice one, right? We can find out. Okay. So let's see. How do we find that? Okay. So for this function, and in the last class we did that. For this function, which is not equal to 1, x, okay, we can find the power series at any point you give to me, right? So for this function, and any number, any point, okay, any a which is not equal to 1, I can show you how to find the power series, okay, and they're equal, okay. So what I'm going to do is, yeah, let me repeat the procedure, right? And this f of x is going to be 1 minus 1, okay? So here's x, right? So I let u to be, remember, right? It's going to be x minus a. So x is going to be u plus a, Okay? And that is going to be 1 minus a, 1 minus u, right? I'm going to find a power series representation for the function. I repeat this again. So this is the important technique we always use. Right? It's a 1 minus, oops, where's the triangle from? It's weird. Oh, link to Shen. Sure. All right, so this term viewed as x, okay? So this is going to be 1 minus a and sigma from 0 to infinity, and just u over 1 minus a to the power n. As long as u over 1 minus a is less than 1, okay? Got it? Yeah. In other words, u is at x minus 1. So it's going to be 1 minus a. And u is x minus a, so to power n. As long as absolute x minus a is less than absolute of 1 minus 1. Okay, so this is my r. Okay, let's rewrite again. Okay, as long as x minus a is closed, okay, for some r. So we do find it, a power series, and this is so the function 1 over 1 minus x can be always expressed as a power series over some interval. How large is the interval you can get? Okay, this is a absolute of 1 minus a. So interval you can get, imagine, okay, this is a line, okay, that's a 1, and here's the arbitrary point a, right? So over the interval, this side, I is going to be absolute over 1 minus a, okay? So the largest interval you can get is this one. The end point touches the 1, okay? Then the function is going to be the 1 over 1 minus x is going to be is going to be given by this power series. In other words, this power series convergent to 1 over 1 minus x, okay, over that interval, okay? So we do have a power series representation for this nice function. So this is so special, we can do that, okay? But for general function, it's not, we're not lucky there, okay? For general function, for general function, okay, how can I do that? On an interval, right? This is some interval. And this interval a is here. It's not necessarily in the center. Can I find one here's a plus r, a minus r? Can I find the power series convergent in a neighborhood of a so that the function is going to be power series, right? So how to find it? I think if such power series exists, that must be unique. I'm going to show you, okay? So suppose that fx is given by this, okay? And here, x minus a is less than r, capital. I have to assume capital is positive, okay? So otherwise, it's not a, yeah. So suppose you have this. Then by the theorem we already learned, you can differentiate many times as you wish. you can differentiate once and get Cn times n, x minus a to the n minus 1, right? Then actually you can start from 1 instead of instead of 0, okay? And you can also re-index it. It's going to be k equals n minus 1, right? Then k start from 0 again. C, k plus 1, k plus 1, and x minus a to the power k. Okay? Then you keep it going like that. The first term is k equals to just C1, 1, right? Then you differentiate again. Right? And then you get a k, x minus a, k minus to the k minus 1. And you can get rid of the first. So look at the first term. The first term, if we expand it, the first term here is C1 plus C2 x when k equals 1. Yeah, C2 and 2a squared and so on, right? Then here, when you differentiate again, you will get 2C2 and I think this will be 3 times 2C3x minus a. Okay, so the leading term, I can, after do some computation, I find out the leading term will be always m factorial Cm and then plus high order x minus a and so on. Okay, so that indicates if you plug a for x, I only have this term, as the rest of them are going to be 0. Okay. In other words, if the function is given, if this power series exists, then you don't have a choice. You must be given by this formula. So that means you cannot have so this includes that every function okay at any point either it cannot be expressed by power function. If it can be expressed by power function, then by that power function is unique, and the coefficients must be given by this. Okay, so what I should say? This is the theorem. Okay, the theorem says that if f has power series representation, okay, for x minus a less than r, and r is positive, then this Cn is nothing but is uniquely determined. So that means the power series is unique if it exists. But this just, but we don't know. If such series exists, then must be in this form. But number one, we're not sure the power series is convergent. Okay, no, we just okay. So this way. So then you get okay. If you are give me a function, then I can compute all the derivatives. Then I get a power series. Then you say this is a power series representation. Then my question is, what is the rate of convergence? Where they're converging to each other, right? And you cannot tell me. You have to check. Okay. So given a function, you can always find the power series, but does not mean they match. Okay. It's a logic, right? This is just a if then. If the function has power series, then the power series must be in this form. Okay. And at any given point, the power series at any given point must be given by this formula Cn equals. Okay. But if you give a function, you compute the derivatives, you still don't know whether this power series is convergent to the function. Okay, so here's my remark. Okay, if you are given a function, differential function can only find derivative on the on the interval I, and a number a in I. Okay, you can always construct. We can construct a power series. We can construct a power series. Okay, no problem, right? You can always differentiate. So question one. What is the radius of convergence? Okay, step two. Second question. Is it equal to f of x a minus r and a plus r? That's two questions you have to solve. Then this is a called, then if answers to both, if you find the radius convergence, then if you can show they're equal, the function is equal to this power series over that interval, then you say that this series is going to power series representation. Otherwise, this is only candidate, does not mean the function has a power series representation. Okay, that's the logic. Then you can say that the function has a power series representation and they're given by that formula over some interval. Okay. So there are some functions that are very bad, and it's differentiable. Okay, it's differentiable as it's differentiable as many times as you want, but the series you construct is not going to be convergent. So the function is not going to be represented by any power series, because the power series you construct is going to be divergent. Okay, I tried to find a good example. Okay, here's the example. Let's see. No, I'm going. Yeah, let's find the. Let's look at this function. Okay, I want to find a power series representation for this function. Okay, that's a go. Okay, so what we're going to do. I have to find a candidate. If it has power series, then the following one must be the power. If it has power series representation, okay, then the following one must be the power series representation. But you have to determine the radius convergence. Okay, so find the. I think I should say find the Z, not F. Okay, find the power series representation because I'm going to specify for this F at A equals 0 at its origin. Okay, those are very, because power series representation, if it exists, must be unique. Okay, so we know that. Yeah. Okay. All you have to do is determine the coefficients, then you tell me what is the radius convergence, whether they're equal to each other, right? Yeah, you have to check the three things. Okay. Let's find out, right? So what we did is if we know this is true for x less than some r, right? R is positive. Then I know the Cn not working very well. Then Cn must be given by this formula. Okay. So let's compute it, right? I know if it exists, if it has a positive representation over some interval around its origin, then this is a coefficient. Okay. So I'm going to find the partial derivative. Find the derivative of e to the x, still e to the x. Second derivative is itself. And then keep it going. You find out the nth or the derivative of e to the x still the same x and never be changed. Right? So f of n at 0, e to the 0 equals 1. So that means Cn equals 1 over n factorial. Right? So if the function has positive representation, okay, then must be the following one. But I haven't found the one yet. I have to verify this is convergent. I have to verify this convergent to the function. That's not easy. Okay. So if the function has a power series representation, then it must be the following. So in other words, if f has the power series representation, at a equals 0, then it must be this. Right? I did not say e to the x equal that because I don't know yet. Okay, I even don't know the radius convergence of this power series, but it's easy to check what is the radius convergence. We just look at this series. The radius convergence of this power series is going to be infinity. Okay. Okay. The radius of the convergence Now why? Well, you can use a ratio test to check using the ratio test. And if you're using ratio test, the limit is going to be L is going to be 0. That is going to be absolute x over n plus 1, which is going to be 0. Okay. So this is always less than 1. No matter which x you choose, so the rate is convergent that. But the question is still, I know this series is convergent for any x. My question is x equal to this for x between negative infinity and positive infinity? Right? We haven't answered the question. We don't know, right? We find the candidate, but this candidate may be not qualified to be. We find a unique candidate. First of all, the theorem says that if it has power series representation, then the candidate is unique. That's it, right? But whether this is qualified, we don't know. We have to verify. But when we look at this candidate, it looks nice. It's convergent over the whole interval. We can easily find the radius of convergence. But still, we don't know whether on the interval convergence, we still don't know it is equal to the function. Maybe on the smaller interval, right? It's not clear. Okay. That bothered some mathematicians in history. There's a guy called Taylor. There are millions of people with the last name Taylor. Okay, we don't know who is whom, right? So only the last name is memorized. Okay, so he find the way to verify. Okay, they're equal. Okay, and that is Taylor's contribution. All right. So what he did? Let's state. Okay, Taylor's inequality. Great. So Taylor says we all want to look at the difference, right? So let's go back to the general case. Okay. So F. The Taylor's inequality. Once you get this inequality, then you can solve the problem. Taylor also could be the first name, right? I remember. That was a student, even female student. His name is Taylor. I was confused at the very beginning. I thought it's the last name. Yeah. It's not used for male student. Male. It's for female. Okay, Taylor's inequality. So Taylor's inequality, he find out, we are assuming all the functions differentiable, otherwise you cannot talk about, right? So he find out if the n plus 1th order derivative is going to be less than or equal to capital M, right? And for x minus a less than d or less than or equal to d, then the difference of this function, which is called n, k start from 0 to k, this is this is a Taylor's. Okay, so this difference is going to be smaller than n plus 1 factorial and x minus a to the n plus 1. This holds for x less than or equal to d. Okay, so let's understand this theorem. Okay, if that is true, we can use that to prove the convergence. You know why? I let n go to infinity, right? If you let n go to infinity, fx is still there, and then you get a power series from k to infinity. But on the right-hand side, if you can prove this conversion to 0, then you're done, right? Okay. So I'm not going to prove this theorem. It's not that complicated. We find a way to do that. Okay. Maybe for the whole life he only did this, but then his name is always in the textbook for thousands of years maybe to come in the world. Okay, because I don't think we can get rid of calculus. Okay, yeah. So earlier days, mathematicians usually from the wealthy families, they have nothing to do, just enjoy mathematics and stay home. We have a farm, big, huge farm, okay, and then sometimes like there are 3 brothers, and the other 2 brothers maybe still work on the farm, and the third brother just enjoy mathematics, stay home because there's enough food for it. Okay, and have private tutors and blah blah blah, and he didn't make, yeah, he just enjoyed doing this. Okay, and we have started here. So, but these days, few 10 years ago, I did some statistics trying to check out who are in the math department, what kind of professors grew up in this country. I found out many of them grew up on the farms. Professors, you can look at the University of Urbana-Champaign math department, like a 90 professors there, and look at those people who age is over 60. Okay, those people. And if you ask them where you grew up, it's not from big city. They're from, from farmers. Okay, okay. All right. So even these days in the world, the majority of mathematicians, they grow up on farms. Maybe you can figure out something, but I cannot figure. My opinion, when they grew up, they had less influence about the world. Okay, they attended the schools in the countryside. Then they enjoyed mathematics because some kids pay attention to it, and teachers encouraged them. Oh, you're great. And then when they went to university, they thought, I'll go to math department, study mathematics. That's it. Okay. If in the city you have get so much information, I should study engineering. It's better. There's so many jobs opportunity. Okay. That's why you choose engineering. Okay. All right. All right. So let's do this. Okay. Let's apply the theorem to we are going to apply this inequality to the function e to the x. How about that? Okay. Okay. And then when you apply it, I have to fix a d. Okay, fix an arbitrary d. Okay, fix an arbitrary d. I don't know. Maybe I change the d later. Okay, arbitrary d. Okay, because in the encoding. So the nth order, n+1th order of the function, which is still e to the x, right? This is less than or equal to e to the d for x less than d equal to d, right? Okay, this is constant. Then, by the above encoding, f of x minus, and this is a k factorial, and x to the power k, because a is 0, right? It's not a n, this is just n. Okay? It's less than or equal to n+1 factorial e to the d and x to the n+1. Okay, this holds for x less than or equal to d. Because this holds for x less than d, I can replace x by d. So it's going to be less than or equal to e to the d n plus 1 factorial and d to the n plus 1. All right. And the important fact is, here's the important fact. The limit of n approaching infinity, n to n factorial, d to the n, is going to be 0 for any d positive. All right. Why this is true? Yeah, this is obvious. So that means this approaches 0 as n approaches infinity, right? Yeah. So that means when you take n version, that means f of x minus n goes to infinity and xk and the k factorial is going to be 0, right? So that means they're equal. Okay, they're equal. So error is getting smaller and smaller. So e to the x is always equal to x to the k and the k factorial for x less than d. But d is an arbitrary, so for any x, that's hold. Okay, so that's why you see it's not easy, but you have to estimate it. Okay. So now we have this formula, for the exponential famous, e to the x power exponential function is going to be very special function, right? We begin with 1 over 1 minus x, but we did not apply Taylor's encoded to find the power series representation for 1 over 1 minus x. We just use the geometric series, to get that result. But now, for other functions, I have to use Taylor's encoded to prove. First of all, I find this pop candidate, right? Then I have to find the radius convergence. I probably don't even find the radius convergence. I just find when it's converging to the function over what interval, because then the radius convergence is automatically determined because it's convergent anyway, right? So these are arbitrary. These are arbitrary. That's why this is convergent for any x. Okay. So e to the x now is given by this power function. Okay. Before I continue to work on the other functions, I'm going to play with this function because I already did that for 1 over 1 minus x, right? From 1 over 1 minus x, we got so many power series representation. Arctangent x, natural log of 1 plus x, remember, right? Okay, or 1 over 1 plus x squared, something like that. So for this one, we can do lots of things too. Okay, so here's a question. Find the power series representation, okay, in the form, this form for for 2 to the x. How about that? Okay, so here's what we're going to do. You can repeat the above procedure, okay, to find the power series. But you can also use the already known result to get e to the power series for e to the x. Okay, that will be much easier. But e to the 2 to the x is not e to the x. Can you change it to the e to the x? Yes. 2 to the x is going to be e to the natural log of 2 to the x. Got it? And that is going to be e to the x natural log of 2. Okay? So this is become e to the some power function. And then according to the theorem, this is going to be 0, n factorial, and x times this. And this holds for any x. Okay? Right? Then.
X, that's only 2. That's as a x right? Like it's Top of it, so it's out of 2dx.
No, I already move it. Yeah, I move x to the side. So this is just a constant times x. The constant is nature log of 2. Okay, so you can write this again, put the constant together, and then here's this. Okay, done. And we not only know this, yeah, we get a power series. We get a power series. This we know this power series converging to the function for any x. Okay, just modify the original function. Okay, here's another question. Okay, find the power series representation for the function e to the x, but this time at a, okay, at a equals 3. Okay, so that means you're looking for the power series in that form. And not only that, you have to prove it's equal to the given function e to the x. How can I do that? Modify it. You let u to be x minus 3. Okay, then x is going to be u plus 3. Okay. So e to the x is e to the u plus 3, is e to 3, and e to the u. And e to the u, you already know it's going to be okay, and this holds for any x. Okay, in particular, yeah, this holds. This always holds for any x. Yeah. So that's easy. That's quick now. Find the power series representation. Okay. In this form for hyperbolic sine x. All right. What you should do for hyperbolic sine x? Right. Hyperbolic sine x is not a brand new function. I said that you can always repeat the above procedure for finding the power series for the e to the x, but I just said that it's a quick way to do that. You can use a given already known result to find the power series representation. Okay. How do we do that? Step 1, you write down this. Okay, and you see that, okay, if I'm able to find power series representation for e to the x, e to the negative x, I'm done, right? So e to the x is going to be, okay, and e to the negative x, you just replace x by negative x. So you got two things. Right? Then put together. All right, so let's put them together. This is going to be half of, right, sigma okay. So you have to group them together, okay? It's going to be 1/2 n factorial, right? And this is going to be 1 minus negative n, and here's the higher. So you will see that when n is even, it's going to be 0, this term. So you can let n to be 2k, or 2k plus 1. Because when n equals 2k, it's going to be 0. So k starts from 0. Okay? And then 1 minus negative 1, it's going to be 2. Okay? 2k plus 1 n factorial. 2k plus 1 factorial. Yeah, just n equals 2k plus 1. All right, then 2 can stop. Right, so this way we get the positive representation for this one, and this holds for any x. Okay, not necessarily for the yeah. This is for any x. So we have yeah. So let's see. Let's summarize, right? We have 1 minus x. This is 2. Right? X is less than 1. We have e to the x. Yeah, we have this 2. Right. So here's the question. Given the function 1 of x, okay, find the power series representation at 2. Yeah, please do it, and I'll give you a couple minutes. Okay, you have to just modify the function. Remember the trick. Okay, so if it's a equals 2, so you let u to be x minus 2 because that's the term you want. Okay, group them together. So then in that case, fx equals, not everybody can learn this trick, honestly. Okay, always at the end, always like a few students that don't know how to do it. Okay, so this x is going to be u plus 2, right? Yeah, because x is going to be u plus 2. Okay, you're going to expand it using the formula I have here, right? So I'm going to take a 2 out. I have to take a 2 out. It's going to be 1 plus half of u, right? 1 plus half of u. But I know the formula 1 minus x. So I have to express it in the form something like that. This is my x. Okay, then I put 0 here. This is x. So it's negative half of u to the nth power. Right. Then I expand it. It's simplified. So you get alternating series. Right. Then finally, and the u is going to be x minus 2 to the power n. So you get the power series. And you have to say the intervals convergence, right? When it's converging to each other, right? When this power series is converging to the function. So when half of u is going to be less than 1. If we expand, it's going to be x minus 2 is less than 2. Okay, 2 is the radius convergence. Okay, that's clear. Why? Because this is a 0, this is a 1, this is a 2, right? This encode represents some interval like that. And you clearly, you cannot go beyond the origin. Why? Because this is 1 of x, right? 1 of x is not defined as 0. Okay, so the largest possible interval you can get is from 0 to 210 to 2 to 4, and which is determined by this encode. Okay, so 1 of x can be expressed as an alternating and power series. Okay. Okay, another one, very simple one. Find the power series representation for the function 2x plus x cubed at a equals 1. Whoa. What is the best way to do? Power series representation, you have to get power series, you have to prove they're equal. So the best way to solve the problem is not to find the derivatives and use the Taylor series encoded. Taylor series encoded only you can use at the very beginning to find to establish those formulas, like e to the x is given by, right, by this, okay? And once that, we just abandon it. We're not going to use it because it's too much work every time, right? So what is the power series representation for this function at a equals 1? Well, do the same way, right? So you let u to be x minus 1, right? Then x is going to be u plus 1, okay? So f of x is going to be 2x, 2u plus 1, and u is, x is u, okay? U plus 1 squared. All right, so we get a polynomial in u. That's all you need. It's going to be 2u plus 2 and u squared plus 2u plus what? This can be written as 3 plus 4u plus u squared. Okay, that's give me 3 plus 4 x minus 1 plus x minus 1 squared. This is power series representation. Polynomial is a special power series representation. Polynomial is power series, it's a special power series. So that's it. You don't need to waste the time to compute the Cn and given by the partial derivative. Just okay. If you yeah. First of all, this polynomial is a power series of the function itself at 0. Okay. Polynomials, power series just generalized polynomials, infinite degree. Okay. If you're given polynomial, you're already given power series at the origin. Okay. If you want to find power series at another point, you have to express it every term into x minus a to the nth power. So that's why you make a change. So f of x now is represented in this form. Every term contains x minus 1 to a certain power. Okay, that is a power. This is a power series representation at 1. Okay. Hey, I'm tired. Let's stop again.